EDX Mechanics 1, Work Energy and Power 3, Variable Resistive Forces. Motion under variable resistance on inclined planes. In dealing with problems on inclined planes, we can take into account the component of the weight parallel to the plane. This would normally be mg sine theta. Now if we think about the work done against this weight, so thinking about the work done by the pulling force against the weight, so the work done against the weight will be this component mg sine theta times the distance it acts, and it acts over the distance d along the slope. If we expand this bracket, we get mg d sine theta, and if we just rewrite this slightly, we can write it as mg d sine theta, and by looking at the trigonometry of the diagram we can see that d sine theta is indeed the height. So you can either deal with the mg sine theta and look at the distance it travels, or you can do work done against the weight is the gain in potential energy. So that's the gain in potential energy. So we have a truck of mass 40 tons working at 200 kilowatts moving up a track inclined at 1 degree to the horizontal. Find the resistance to motion of the truck at the moment when its speed or velocity is 15 meters per second and its acceleration is 0.1 meters per second squared. So again, we're taking a snapshot of the journey, and at this snapshot it's travelling at 15 meters per second with an acceleration of 0.1 meters per second squared, and we want to know how big the resistive force is. So we can use our power formula. Power is the tractive force times the speed. We know the power is 200,000 watts. The tractive force we can find, and we know that at this moment the speed is 15 meters per second, which gives us a tractive force of 13,333 newtons. We have the instantaneous acceleration, so at this moment we can do Newton 2 up the hill as well. So the force acting up the hill, we have a positive Ft. However, we've got Fr, the resistive force acting down the hill, so that's negative. And using the component of the weight, remember that the angle in there is 1 degree. The component of the weight is 40,000 G sine 1 degree. That's also acting down the hill, so that's negative. Equals the mass, which is 40,000 kilograms, times the acceleration, which at this moment is 0.1 meters per second squared. So we know Ft, we can substitute for Ft. We can substitute Ft into this method, and we can find the resistive force is 2,492 newtons. As we can see there. In this problem, we have a car of mass 4 tons working at a constant 40 kilowatts, moving up a track inclined at 5 degrees to the horizontal. We're given that the resistance to motion is equal to 150 plus 10V, so you can see the resistance varies with speed V. And we want to find the maximum speed of the car up the track. So the key thing to spot here is we are talking about the maximum speed. So if this car has reached its maximum speed, then the acceleration will be 0 and the forces must be in equilibrium. So maximum speed tells me the acceleration is 0. So when I do Newton's second law up the track, we know there's no acceleration. So we've got a positive tractive force, Ft. We've got a negative resistance force, Fr. We've also got 4000 G sine 5 degrees, using the 5-degree angle in there, and that's negative, and we know that that total force must add up to 0 because at maximum speed there's no acceleration. Now, using power is Ft times the speed. We know the power is 40,000 watts. Ft we're looking for, and the maximum speed is v. So if I rearrange this for Ft, that's the thing I'd like to be able to use later on, I get Ft is 40,000 over speed v. So we've got Ft. Fr is given in the question, so I'll just write that down again as a reminder. So the resistive force Fr is 150 plus 10V. So we have the resistive force, we have the tractive force. So now when we revisit equation 1, we've got Ft, which is 40,000 over V. We've got a negative Fr, which is 150 plus 10V. And we've got minus 4000 G sine 5, must add up to 0. So if we multiply through by V at this stage and tidy up the terms, we will get 0 equals 10V squared plus 3566.5V minus 40,000. So I've multiplied all the way through by V and collected like terms, and I can now solve this quadratic using a quadratic formula or a scientific calculator to get the speed at this moment is 10.9 meters per second to 3 significant figures. So the thing to remember, at maximum speed there's no acceleration and the forces parallel to the plane must be in equilibrium. So that tells me that the tractive force Ft can be written as Fr plus 4000 G sine 5. And if I substitute for Ft and rearrange by multiplying through by V, we can get to the quadratic in V. So useful to know that you can solve this quadratic using an enhanced scientific calculator or graphical calculator, many of which will solve quadratic equations to get the answer 10.9 meters per second. And that brings us to the end of variable resistive forces.